example number 8. You're looking at the following data was obtained from analysis. Carbon 40%, hydrogen 6.7% at 760 millimeter mercury pressure and 200 degrees C. 10 milligram of the compound occupies a volume of 6.47 mils. What is the molecular formula of the compound? Remember, the data was obtained from analysis that 40% was carbon, 6.7% was hydrogen, and then at 760 millimeter mercury pressure and 200 degrees C, 10 milligram of the said compound occupies a volume of 6.47 mils. What is the molecular formula of the compound? Now, in this kind of scenario, if you see where a little bit complication, it looks somehow, but it's not. It has very, it is simple way to get your molecular formula. But first of all, before you arrive at your molecular formula, you must first of all get your empirical formula, because it is through the empirical formula you can then arrive at your molecular formula, knowing, of course, our rules of our empirical formula and molecular formula rules. So let's see what plays out from there. So if we look at this, see the solution to this question 8. Now, carbon percentage of the given, you have C 40, and of course hydrogen. So we have 40% of carbon, and of course we have 6.7 of oxygen. Sorry, of hydrogen. Now, if you sum this together, we are going to be arriving at what? 46.7. So a total of 46.7. So for us, the remaining of this is oxygen. So it's going to be 100 minus 46.7, because this percentage summation is not up to 100. So the balance that will make it up to 100 will be that of oxygen. So if you do this mathematics right now, if you do this mathematics, you are going to be arriving at 54.3, 54.3%. So that equals to oxygen automatically. Over the right there. Yeah, look, 53. So the ratio of oxygen will be 5:3. So when you do that, you divide it by the relative atomic mass of carbon, which is 12, and of course that of hydrogen is 1, and then of course that of carbon oxygen is 16. So if you strike this out, you have 6.7 here. This 12 by, of course, by that will give us 3.3. And of course, this one was 3.31. So you divide through by the smallest, and divide through by 3.31, 3.31, and then of course, you divide through by 3.31. If this strike this, you should strike, you will have 1. This into this, of course, you are going to be arriving at 2.02. 2.02. And when you strike, it will give you to us 1.01. 1.01. So, looking at this rule, you can multiply through, of course, because multiplying through by any whole number will not give us a whole number. So, you have to apply the rule of rounding up and rounding down. So, here we're rounding down to 1. Round this down to 2, and round it down to 1. So, we have this. So, to do that, our ratio, our E dot F, which is our empirical formula, by this is going to be C H2O. C H2O. So that's our empirical formula by this. But that was not what we are asked to get. We are asked to get the molecular formula of that. And then how do we get the molecular formula? Knowing too well that the molecular formula rule must pass through the formula of that E dot F will be equals to M dot F divided by N. So if we are making M dot F our subject, because that's our main aim, that will give us E dot F bracket N. That N is the whole number. How do we get that? We are already gotten our E dot F. So what we need is the what? To get the molecular mass of the compound. So let's see how it goes. Now how do we get that? Recall that from the question, they said that the compound had at 760 milliton mercury pressure and at 200 degrees C, that 10 milligram of the compound occupies the volume of that. Now, looking at that, putting all that together, we are going to be recalling that there is a relationship between the number of moles with ideal gas law. And so, going through, recalling that ideal gas law has all these properties. Remember that our empirical formula from the calculation, that our E dot F is equal to CH2O, already done. So recalling that to get our molecular mass, we are going to go to that ideal gas law. The ideal gas law will be applied to this. Using that, we are going to recall that PV is equal to nRT. So knowing that N will be equals to PV all over RT. Now, our N is mass over molar mass, which is equals to PV all over RT. If we know this, that simply means that we can say that our PV will be equals to mRT square. So from here, we can deduce vividly that M, a main subject here, and that will give us as mRT all over PV. So we can get our weight here, molecular weight, from here. So we have our mass. The R is constant, which is of course 0.0821 gas constant. Our temperature is given to is got from the question. Our pressure as well is given to us there at 760 milliton mercury, and then volume is given to us at 6.47 mil. So from this formula, we can move on. But also recall that this formula can also lead us to density, in case it was density. Maybe it was said in the question, we recall that density was given. Density of the gas was given. If density of the gas was given, you can record this formula can lead to it, because we know that mass over volume there is density. You can record that, and then of course we arrange our formula from the ideal gas law and then arrive at density. But this formula is suited to getting our molecular weight of the compound. From here, we can reduce it to our formula M dot F, which is equal to E dot F times N. Alright, so going back to that, from that formula, you can recall that n will be equals to small n all over RT times PV. So doing that, we'll be having the mass there, converting it to milligram. That will give us to grams. That will give us 0.01 gram. The gas constant times R is 0.0821 atm dot liter per liter per mole per Kelvin. And then temperature, if you must convert that to Kelvin, converting 200 degrees to Kelvin, we'll be having 273 to that. That will give us 473.15 Kelvin. You do that, divide all through. Of course, our pressure there is limited to 760 millimeter mercury, which is directly equals to 1 atm. So we have 1 atm pressure there. Of course, times volume. Convert our volume there from mils to liters or dmq. That will, of course, you are going to divide that by 1000. That will give us 0.00 0.000647. That will give us liters. Now, let's see. ATM, we go with ATM. Per liter, we go with liters. And of course, per Kelvin, we go with Kelvin. So we'll be left with grams per mole, which is the molar mass of that. So if you do that mathematically, you're going to be arriving at 600.40 grams per mole. Now, knowing too well, we have gotten the molar mass there. We're going to be inserting it into that. So by our formula, we're going to be deducing our M there. So our M dot F will be equal to E dot F or a mole, which is equals to 600.40 grams per mole. Okay, we already know from our empirical formula that getting the empirical weight here is going to be given to us as 12 times 2 plus 16. That will be 28, that will be 30. So we have that empirical weight will be 30 brackets N, which is equals to 600.0. So doing that, our N here will be equals to 600.40 all divided by 30. To do that, we will add 20 as our N. When we do that mathematically, we have an N is equal to 20. So when N is equal to 20, we say that the molecular formula equals to empirical formula times N, which is 20. So when you do that, you'll be having C20 is 40 and O20 as our N dot F. Thank you.